webinar. Let me get a few things set up on my end really quickly. All right, so good evening, everybody. It's great to see a good crowd for our first webinar of the evening, or for the webinar this evening. I guess not the first webinar of the evening. Anyway, my name is Crystal Partica, and I'm the project manager for the Northern Grapes Project. Today's webinar is The Big Chill, Cold Acclimation and Recovery from Spring Frost in Grapes in New York with Tim Martinson and Jason Londo. Jason is a research geneticist with the USDA ARS based here in Geneva, New York. His research is centered on understanding the genetic and phenotypic aspects of environmental stress tolerance and adaptation. Tonight, Jason's going to talk about bud dormancy and cold hardiness in grapes. Then Tim Martinson's going to take over and talk about some of the work that we're doing up in Clayton, New York, focusing on recovery of Frontenac after a devastating late spring frost. Tim is a senior extension associate at Cornell University and leads the statewide viticulture extension program. He's also the director of the Northern Grapes Project. So with that, Jason, I am going to, oh wait, a couple of announcements first. Remember that as a participant in tonight's webinar, we ask that if you have a microphone, you please keep it muted. If we get too many microphones turned on during the course of the webinar, it makes it really difficult to hear the presenters. So please keep those microphones muted. Any questions or comments, or if you're having technical difficulties, please type a note in the chat pod on the lower right-hand side of the screen. We'll take a break in between Jason and Tim's presentations for some questions, and then we'll have time at the end as well. So Jason, I'll let you get started.
All right, thank you, and welcome everybody. Thanks for having me on tonight. So we're gonna get right down to business. We're gonna talk about how grapes deal with winter. And I'm hoping to answer some questions by the end of this talk about how winter temperatures influence grapevines, what is cold hardiness and what is dormancy, and how do climate, genetics, and geography interact to encourage or discourage different varieties in different regions, and can we plan and breed for a future where we might have climate change? So to start with, we're going to go with Vitis vinifera. This is the cultivated species of grape. It represents about 95 to 98% of the industry worldwide. Vitis vinifera is a Mediterranean adapted species because it was domesticated and evolved in the Mediterranean region. It was domesticated from Vitis vinifera sylvestris, and Sylvestris's native range is pictured here in the gray area around the ring of the Mediterranean. Now, if you look at what temperatures in winter look like in the Mediterranean, that's what's up here in this top map. You can see all the reds and dark oranges. So the Mediterranean is very mild. We're talking temperatures that maybe reach freezing, at maximum getting to -7 degrees Celsius. As a result, vinifera is adapted to nice, cool, mild winters and warm, dry summers, and is not adapted to survive in winters that we experience here in North America. So if you look across the varieties of Vitis vinifera, those with the greatest hardiness, things like Riesling and Cab Franc, they can survive temperatures as low as -22 to -25 degrees Celsius, depending on the winter. But beyond that, they're pretty much killed by any winter chill. Now you can contrast that with a wild grapevine species from North America, Vitis riparia. In the bottom left-hand corner here, you can see a distribution map. You see that it grows all the way from Louisiana and Texas up to the Canadian border, and it actually extends far to the north of the Canadian border. If you compare that to the temperature map on the right, you can see that none of that area is Mediterranean. Very little of it is red at all. Most of it is yellow and blue, so much colder winters. As a result of growing in these regions, for its evolutionary history, it's adapted to cold, harsh winters. It can survive temperatures as low as -35 to -40. But I also want you to notice that its distribution is not only northern. It extends all the way down to Louisiana, where it's much warmer. So it can also tolerate cool, mild winters. So if we're talking about growing grapes outside of Mediterranean regions, we need to think about how we breed with wild species to include adaptive traits. So Vitis riparia is just one of about 20 different wild grapevine species we have here in North America, and one of another 40 that you can find in Eastern Asia. In North America, we tend to use a lot of these wild species for breeding programs, for cold hardy grapes, but also for rootstocks. And you may be familiar with these species, but Labrusca, this is where your Concord and Catawbas are coming from. Cinerea, Estivalis, Vulpina, and Rupestris are all used both in some scion breeding and in rootstocks. And down in the bottom right corner is Vitis amurensis. This is the sort of Vitis riparia of Asia. It's the cold hardy species from that region. It gets used a lot in Eastern European and Russian breeding programs, as well as the Chinese. So we need to incorporate traits from all these wild species because we grow vinifera outside of that Mediterranean habitat. But we also have to think about incorporating traits because our climate is changing. This is a map of the grapevine production regions across the globe. And in red are areas that are currently suitable for Vitis vinifera growth. But those areas are also expected to disappear due to increasing temperatures. So the blue areas represent where we think temperatures will be more amenable to grapevine growing in the future, and in this case, it's 2050. If you zoom in on a couple areas, in California, you can see here, this is current day. Anywhere you see color is where a grapevine can be grown. But in the future, you can see this big swath of the Central Valley is now inhospitable. This is due to too much heat. Similarly, here in the Mid-Atlantic and Northeast, you can see a movement of this from this red area, northerly into Canada, Michigan, and some of the higher regions of Pennsylvania and New York. And in Europe, some of the most famous growing areas, Douro, Bordeaux, Burgundy, and Tuscany, are all expected to be very difficult to grow grapes in the future. It doesn't mean that we won't be able to grow grapes there, just that the conditions are changing and it's going to become more difficult. So what we do know about a warming world is that it's also going to impact cold. We're expecting overall to have warmer winters, particularly in the north, but more importantly, changes in temperature patterns and changes in precipitation patterns. And this impacts how our winters occur, most obviously in something called the polar vortex, which I'm hoping everybody's very familiar with. We had this 2 years ago in the middle of the winter. The polar vortex is a natural occurrence, but it's predicted to become more frequent. And that's because as temperatures increase across the globe, they're increasing mostly in the poles. In a normal cold pole, warm equator situation, the jet stream keeps all that cold air trapped up at the pole. But as we have a warming climate, the pole gets warmer and this jet stream gets kind of lazy and it starts swooping up and down through our country. We don't have any Himalaya mountains to block air. You can see that very clearly here in this heat graph of the polar vortex 2 years ago. So you can see that big trough. So we need to be thinking about a changing climate, not only in that we're going to be losing some areas due to heat, but in marginal areas like where the Northern Grapes Project grows grapes, we're going to experience more erratic weather. So we need to have a better understanding of how grapes tolerate cold and figure out how much room we have to breed with. So cold hardiness is a very complex trait. It impacts lots of different tissues, the buds, the phloem, the xylem, and the cambium. All these tissues have to survive winter. Today we're talking about the buds primarily. There's also genetic, physiological, and mechanical defenses that the vines deploy in order to survive freezing. And depending on when the freezing events occur, it can cause different changes in the plant metabolism. So if you have frost in the early fall before the vines are fully acclimated, you can kill the canes. As you can see here, the light canes are dead. If you have polar vortex events or other cold extremes in midwinter, you can simply surpass the vine's defenses and freeze it to death. And then in the spring, if you have early spring bud bursts, you're also at risk of frost. During this entire time, the primary defense is dormancy. The vine needs to be dormant in order to gain cold hardiness. And that's basically because growing tissues do not tolerate ice very well. So if we review dormancy real quick, during the growing season, a lot of buds are dormant. The buds here at the base of all these leaves are dormant, and they're held in a state of paradormancy by the tip. So as the tip is growing, it pumps hormones back along the cane, keeping all of these quiet. So that's paradormancy. In the fall, light changes and temperature changes move the vine from a paradormant state to an endodormant state. And you can most obviously see that in the vineyard by the progression of paraderm down the cane, from the base of the cane to the tips of the cane. So these buds here at the base of these leaves behind the ripened wood are all dormant, and they're called endodormant. If you were to lop this cane off and put it in a growth chamber, the buds would not grow because they're held by some sort of internal molecular metabolic block, the endo or inside dormancy. We don't know what fulfills that dormancy, but at some point during the winter, the buds move to a state of ecodormancy. And this is the case where the cold temperatures simply keep the bud from growing. So that's an environmental form of dormancy. Finally, in the spring, we get enough warm temperatures, growth resumes, and as long as we don't have a frost event, the life cycle starts over again. So we're interested in these different parts of dormancy because they overlap with different parts of acclimation and deacclimation and freeze hardiness. In the fall, when vines begin getting to be endodormant, they gain an ability to survive freezing temperatures called acclimation. During the middle of winter, they gain the most hardiness. They're able to survive the lowest temperatures. And then in the spring, they deacclimate at a rate that's faster than they acclimated in the first place. And overlaid on top of this is that whole endodormancy, ecodormancy transition. So something happens here in the middle. And we're working on figuring out what that is. That's important because the acclimation process is a balance between non-lethal and lethal freezing. You can have both forms of freezing in any given winter. A normally safe winter, only non-lethal freezing occurs. So here in the compound bud of grapes, you've got the primary bud. This is where your fruitful clusters come from, secondary and tertiary. If you were to zoom way in, this cartoon is supposed to represent different cells, grapevine cells, and the ice crystal in between is the type of ice that forms around -5 degrees Celsius. This is safe and non-lethal. However, as temperatures drop, that ice adds more and more stress, and when the interior water inside the cell freezes, it kills the plant, and that's the lethal freeze. So that's what we're trying to avoid. We can assess whether something has had a lethal freeze by cutting buds, so going out and collecting canes. This bud is totally alive. This bud has lost the primary, and this bud has lost all 3 buds. Or we can assess it in a way called differential thermal analysis here in the lab by excising the buds from the dormant cane, putting them in this into this plate, into this chamber, and then slowly freezing them and measuring when that internal water freezes. What that looks like is shown here. So this is decreasing temperature right to left. As the plate is cooling, you get this non-lethal freezing. This is the safe freezing. As temperatures continue to drop, you reach a point where the buds start dying. And each of these little peaks indicates a bud dying. The water's freezing inside. This is the lethal freezing we want to avoid. But we can use this to predict how bad winter is damaging our vines. So if we take the mean of these peaks, we get something called the LTE50 or LT50. And in this case, we would say that this vine could survive till -21 degrees Celsius. So we can use this method to look at how winters impact grapevine hardiness and how different varieties respond to different winters. And it's interesting to think about, but winters are not all created equal. So here in New York, this is the temperature data for the last 3 winters. The first one is a mild, cool winter. The red line here indicates the freezing point. Blue beneath that line indicates time freezing. Black above that line indicates time above freezing. So you can see just by quickly glancing at the colors that in this first year, we had lots of cold weather, but it was pretty mild. In 2013, 2014, we had a lot of severe cold events, but a lot of big swings in temperature as well. Very cold, very warm, very cold, very warm. And finally, in 2014, 2015, we had an equally cold winter, but instead of oscillating above freezing, we just had the sustained cold. As a consequence, we had no freeze damage in 2012, 2013, extensive damage in 13, 14, and patchy damage in 14, 15. And that's because the LTEs change depending on the year. The vines are responding directly to the temperatures they are experiencing. It isn't an all or nothing. If we look at different wild grapevine species, that's the name of the species pictured here. Here's hybrid. You can see that different species are able, in the same time point, mid-December to February, to have different lethal temperatures. Similarly, in different winters, they're able to change their lethal temperatures. So in the 2 colder winters, you can see that all of these numbers decrease. So winters aren't equal, species aren't equal. For the sake of simplicity, we're just going to look at hybrid and the 2 cold hardy species, Amaranthus and Riparia. So if we chart those LTE values throughout the whole winter, you get a curve like this. So here's the minimum temperature. Here are the LTE curves. You can see that the hybrid, amurensis, and riparian are all equally hardy until about midwinter, and then you have this little bit of loss of hardiness in amurensis. That's because amurensis is responding to this heat event. If we look at the cold winter, now we see the hybrid is less hardy. The riparian and amurensis are more hardy, and you can again see riparian response to this heat event. And in this year, we actually sustained quite a bit of damage in amurensis and hybrid varieties. If you look then at 2014, 2015, you see a much different change in temperature. A decrease in temperature overall leads to this swoop in hardiness. So you can see here, the hybrids are still the least hardy, but amurensis and riparian are much more hardy. So the type of winter determines the extent of bud cold hardiness. Similarly, the buds don't gain maximal hardiness unless the winter conditions are severe. So here, this dashed red line indicates the maximal hardiness in the warm year, and the bottom dashed line indicates the maximal hardiness in the very cold year. So you can see they don't gain the maximum hardiness unless they have to. So assessing LTE is both location and year dependent. If we look at Vitis riparian, that widely distributed northern adapted species, I looked at 43 different genotypes that grow here in Geneva, and you can see throughout the winter that there's over 10 degrees Celsius range in variation at any one point in the winter. So there's tons of variation in how these vines respond to temperature. I also want to point out that in each year, if you just take a temperature cutoff of negative 32 degrees Celsius, that there are both northern varieties and southern varieties that are extremely hardy. And so this isn't only that northern riparian is cold hardy, it's the entire species. Okay, so that's cold hardiness. That's all going on underneath this bubble of dormancy. So buds require a specific number of hours of cool, but not freezing temperatures in order to be ready to grow in the spring. This is called chilling hours. Once you get enough chilling hours and the buds are ready to grow, they require a certain amount of heat. These are the heating hours. And it's the balance between the chilling hour fulfillment and the heating hours that lead to the rate of bud burst in the spring. Different species and different cultivars have different chilling hours and different heating hours. Today we're just going to talk about chilling hours, but basically you need to know that these two things interact with one another. If we look at the average number of chilling hours that occur across the United States, this is what I'm showing here, a contour map. This is the total number of hours between 0 and 7 degrees Celsius that occur on an average year. If you look in the northern plains, where we have very, very cold winters, that most of the winter is spent below 0, you have very low chilling hours. And that's because the time spent between 0 and 7 is only in the fall and in the spring, and then little heat waves in the winter. However, if you look at in Michigan, New York, Pennsylvania, we have a lot more chilling hours. And that's because our winters are modulated by the Great Lakes and the Atlantic Ocean. So that raises our temperature into that sweet spot. In the middle of the country, they have a whole bunch of variation depending on the winter. And so you tend to have this big open contour. So chilling hours are different based on geography, and that's due to the climate in that area. And to remind you, chilling hours accumulate between 0 and 7. It is thought that temperatures above 7 degrees Celsius may actually rewind the chilling hour clock, and temperatures below 0 are essentially invisible. So when you look at what that looks like in 3 different regions, here's Missouri, New York, and South Dakota. In the warm year, you can see that Missouri and New York have a lot more chilling than South Dakota. If you look in the cold year, you see the lines are closer together, but you still have the same pattern. And in fact, if you total it up at an arbitrary spring date, just say April 6th, you can see exactly what I'm saying. South Dakota has a lot less chilling on the same date as in the other regions. Additionally, you can see that in the warmer year, those numbers are higher. So if we use the fact that there's a warm year and a cold year as sort of a model, in a climate where we have increased winter warming, we're expecting to see increased chilling hours. So this might not sound that bad. A nice mild warm winter might be something that we could all be happy with. But from the vine's point of view, it can actually be kind of dangerous. So here is the chilling hours in Geneva in the last three winters. Just to remind you, we've got a mild winter, a cold winter, and a cold winter. And you can see the chilling hour accumulation in the mild winter was much higher at any one point after, say, December 14th than in the cold years. So this becomes important if you have a variety that, say, requires 1,200 hours of chilling before it'll burst. You can see here it would occur somewhere towards the end of March, would be ready to grow, whereas in the cold years it would be much later, late April. If you look at what we had for bud bursts and frosts in those 3 years, we did have early bud bursts in 2012, and we had a very bad frost in early April that did a lot of damage on early cultivars, early varieties, and early species. We didn't have that same scenario here in New York in the cold years, and that is partly due to the fact that the vines simply didn't have enough chilling to be ready for full bud burst. So warm, mild winters are dangerous because the vines are super chilled and can burst faster. We can measure the differences between species and the differences between cultivars and varieties in their chilling hours by a very simple experiment. You just go out, cut a bunch of vines from the field, put them in a cooler, and take them out after certain amounts of time. And what you get is this relationship. In the early part of winter, when there's no chilling, the buds take a lot longer to burst, so these are days needed to burst, than if you give them, say, 2,000 hours of chilling. You can see that they all get faster. We want things to get enough chilling so that they burst synchronously in the field. So if you look at this line here, 50% bud burst at 4 weeks, this is a good indicator for when something has fulfilled its chilling. If you take these vines at 750 hours, Cab Franc and Riesling, put them in cups of water in the greenhouse, they all burst very synchronously. But if you put Cab Sauv, which has not reached its chilling point, you get very desynchronized bud burst. So it's important to understand chilling hours because we want things to get chilled to the point where they'll synchronously burst, but we don't want them to be super optimally chilled on this end, where they're going to burst really fast as soon as we get a warm day. If we look across grapevine species, we see that relationship is the same. Basically, the slopes of all these lines are more or less the same. They all respond to chilling in the same way. So all species need chilling to synchronize bud burst, but there are different requirements for chilling between species. You can see here I've put an arrow with southern and northern, and that's a general trend in that southern species tend to be higher chill, northern species tend to be lower chill, and this makes a lot of sense based on where these species have adapted to grow. Winters where you don't have a lot of chilling and winters where you have a lot of chilling. It's also important to note that all species can also be over-chilled or super optimally chilled. So all species are at risk given enough cool temperature. If we look again at riparia, because we all like to use riparia in the north, these are 43 lines indicating the bud burst rates for riparia. And I colored them by southern and northern again, just so you could get a general idea. Basically, we see that southern varieties respond in the same way as northern varieties, or genotypes, whatever you want to call them, but they tend to be a little more resistant to the chill in that they require a little more cold to reach that 28-day bud bursting time. So it may be important when you use riparia in hybrid breeding programs to sample some southern genotypes, because you could possibly avoid breeding for rapid bud burst. Or you could perhaps branch out and use other riparia or non-riparia species. We have a lot of good species that have good cold hardiness and much, much higher chilling requirements. Okay, what does this mean for grape production and for new cultivars? So basically, chilling hours determines bud burst synchronicity and bud burst speed. So we need low chill varieties in the north because the winters are low chill. If we plant high chill varieties there, you won't get synchronous bud burst, you won't get synchronous flowering, and you'll have patchy ripening. The problem is that if you plant those same low chill varieties in places like New York or Missouri or places that have much larger dose of chilling hours, those varieties are at high risk of superoptimal chilling and subsequent frost damage. They're going to come out of the gate so much faster simply because they've been waiting so long. So pictured here are just some examples from data that I've collected here on Cab Sauv, Concord, Cab Franc, Riesling, and Merchel Foch. These are the chilling hour requirements under my conditions for those varieties. So if we plant those out in Missouri and New York this in 2012, 2013, and look at whether or not they got enough chilling, you can see that all 4 varieties were synchronized. They got enough chilling to be synchronized, but Concord, Cab Franc, Riesling, and Marshall Foch were all overchilled. And if you look at Marshall Foch, it is massively overchilled. Marshall Foch here will sometimes burst in 3 to 7 days. Contrast that with South Dakota, and you can see that Cab Sauv is not getting enough of its chilling, even by mid-April. So if you plant Cab Sauv, if it could survive the winters, it would be desynchronized. Concord is okay if it's late spring. Cab Franc, Riesling, and Marshall Foch are all synchronized. So you can see the varieties are going to make a very big difference when it comes to chilling on how successful you are in different regions of the country. Riparia-based hybrids are likely to also be at risk to spring frost because they're coming from stock that have low chill phenotypes. So things like Marquette, Frontenac, St. Croix, and others could have this low chill phenotype. And I have not sampled them. It's on the plan to do. So I'd be very interested in seeing what people have experienced with bud burst rates with these different varieties. However, there's lots of variation in chilling hours if you branch outside of riparia, well into the 2,000, 2,200 chilling hours. So if we're breeding for a warmer, less stable future, we need to consider expanding our chilling hour requirement in new varieties. So now this is a little made-up scenario that I did just to illustrate how climate change might impact chilling hours. So pictured on the right is a map of the US and Canada, and that red overlay is the most conservative estimate of how climate temperatures will change by 2070. And you can see it's an increase of 2 to 3.5 degrees. So if you look at our chilling hour requirements in 2012, 2013, so here's South Dakota. By the end of April, here's New York. If you add 2 degrees Celsius, you move the line to the top here and to here for South Dakota. So you can see that New York actually has less chilling hours in the fall because they're warmer, but then it quickly regains the chilling hours and surpasses the non-climate change scenario. South Dakota has the same chilling in the fall, but then you see this, it expands towards the spring. If you take an arbitrary date, say March 30th is when we're starting to think things might get ready to burst. In New York, that's an additional 400 hours. In South Dakota, it's 250. If you back compute hours, you see that 100 hours of chilling actually moves your bud burst up 1.3 days. So this is an average of 5.1 days faster in New York and an average of 3.2 days faster in South Dakota. And that might not sound like a huge shift in phenology, but it makes a huge difference if the frost occurred two days before this point. So if we look ahead now to 2015, 2016, this is the prediction on what our US winter will be. They're expecting us to have a much warmer winter. Again, this might be really nice for us, but for the vines, this is going to subject them to more chilling, similar to the way I've shown in those graphs. So if we do have this warm winter, we need to be very wary of frost damage in the spring because there's going to be a higher risk. So just to conclude what I've gone over, winter extremes are more likely to happen if we have a warmer pole and weakened trade wind system, and that's the way that projections point. So bud hardiness needs to be retained because we're still going to have those polar vortex situations. It's not a foolproof system. Warmer winters are going to overchill grapevines in northern growing regions, and that may lead to increased risk for frost events. Acclimation, midwinter hardiness, dormancy, and bud bursts are very complex, and they all overlap with one another. But the differences are driven by both genetics, so what we can do with different cultivars, different species, but also geography and climate. And we need to select for both midwinter survival and chilling hour based on climate. Maximal hardiness is determined not only by the cultivar, but also the type of winter. So this means damage from severe midwinter cold events are very difficult to prevent. There is no sure thing. Cultivar choice can help, but it's not possible to prevent all damage in all years. And all wild species have potential for breeding. Chilling hours and dormancy level along with spring temperatures determines your frost risk. This risk is different based on geography. Finally, Climate change is projected to result in warmer northern winters. This will increase the amount of hours we have for chilling hour accumulation, which will also lead to super optimal chilling of all varieties, no matter what you plant. They will get better at bud burst. Hybrid varieties with low chill pedigrees may be at higher risk of frost damage because of this combination of genetics and climate. So things like riparian amurensis-based hybrids are going to be at the highest risk because they are at the lowest chill end of the spectrum, but they really do need to be looked at in different regions because different local site microclimates can have impacts as well. And finally, breeding programs shouldn't be afraid of trying southern species. We see in the southern species here in New York that they have very good cold hardiness and much wider range in chilling hour requirements. And so I think there's some potential there in incorporating southern species for northern grapes. So with that, I'm going to just say thank you to the USDA folks here who helped me, the Cornell folks that I work with, Bruce Reich, Tim Martinson, Chris Lynn. We all try to do our best here to make sure we have the most cold hardy grapes. Also Ann Fennell at SDSU and Michaela Centenari at Penn State. And I know I covered a lot of stuff, but I'm hoping that it was clear, and I'm happy to answer any questions.
Thanks, Jason. We've had a few questions come in. One that Tim and I kind of answered in the chat pod, so we'll move on to another one. Okay. Bill asked, how are growing degree days related to chilling and heating hours? Growing degree day information is readily available on weather websites, but the others are not.
Yeah, that's a great question. So the growing degree days plays into those heating units that I mentioned earlier as part of that two-part equation for when things burst. What we're finding is that there's variation in how different species and possibly how different cultivars respond to growing degree days. So I don't have it simplified yet where we can say this amount of chilling plus this amount of heating equals this amount of bud burst, because they're both dynamic processes. So as to what are you supposed to do for guessing about bud burst using only growing degree days is you could look back at historical records and use that as a reference. But you're going to have to wait for me to get a little bit more work done to push this chilling hour as a component available for growers, because it is a very important component of how primed those buds are for that heat.
Okay.
I hope that answered it somewhat.
Yeah. Bill, if you can let me know in the chat pod if you have a follow-up question. Then Link asked, please review why the winter 2 years ago there was more vine damage compared to last year, even though last year's winter was overall more severe.
Right. And now, mind you, I can speak to New York because I've looked at New York's weather and New York vines, and so this may not be able to be passed over the whole northern grapes area. But in New York, the reason that it occurred is the way that the cold events and the heat events occurred in those 2 winters. So 2 winters ago, it got down to -25°C and then went back up above freezing the next couple days. It stayed warm a couple days, and then it dropped way back down, and it oscillated throughout the whole winter. Whereas last year, we went down to the same temperatures here in New York, -25°C, but it never oscillated above freezing. In fact, we were below freezing for like 2 months straight.
Way too long.
Way too long. But that's actually perfect for the vines, because those vines, they're chilling and they're getting ready for spring. And when they see that heat, they start to respond. And one of those responses is to lose some of that hardiness. So if you have a very sustained cold winter, the buds sort of are blind to the fact that temperatures are going up 20 degrees because they're all below freezing. But when temperatures go very, very cold, very, very warm, very, very cold, very, very warm, it sort of confuses them. And so that primed our vines for a lot of damage because a lot of them deacclimated just before we got the major cold event. And so we had much greater damage.
Okay, and then Link had another question. You said that bud burst is dependent on chilling between 0 and 7 degrees Celsius and heat events. What is the temperature range for the heat phase?
Yeah, again, that is something we're working on. And I will couch this a little bit. The chilling temperature between 0 to 7 depending on which models you use, it's 0 to 7, 0 to 10. It's in that range. And it may be that different species and different cultivars have different sweet spots in that range. Similarly, on the heat side of things, we're finding that the northern species tend to respond faster to low temperatures than, say, vinifera. So the temperature range for the heat phase is also variable and also dependent on species. So things like amurensis actually start losing hardiness and getting ready to burst at 4 degrees Celsius in late winter, whereas viniferas and riparias do not. There's something about the genetic makeup of amurensis that species responds to much, much lower optimal growing temperatures. And so we're working on that to try to come up with a way of then evaluating hybrid grapes for these different parameters. What is their optimal chilling temperature? What is their optimal growing temperature? So it's a work in process.
Thanks,
Jason. Before you go, I have another observation for you.
Okay.
Our plant pathologist, David Goodori, and some other people have found that in places like Australia or maybe the Central Valley of California, that bloom is much less synchronized. It might occur over a period of 2 or 3 weeks, and this has implications for disease management. And so whereas in New York, often if we have the weather's right, it occurs over to 3 to 5, days, basically, depending on variety. And so is this the same phenomenon that has to do with chilling requirements? I think what they related it to was the mean temperature in the coldest month of the year.
The mean temperature in the coldest month of the year. I would just say yes, it has something to do with the chilling requirement. If you look at what the chilling level is in a lot of the Californian production regions, it's a lot lower than we have here. Right. And so if you don't have enough chilling, you will still burst and grow. And the closer you get to that perfect spot, the more synchronous you're going to get. But if you don't reach that sweet spot of chilling, you will be desynchronized. And it makes total sense that in a climate that's much warmer and has much less chilling, that varieties, particularly something like Cab Sauv, is a very high chill cultivar of vinifera, requires 1,250 hours. So if it doesn't get 1,250 hours, it's going to take much, much longer for a given field to fully burst, which means you're going to have different flowering across the whole field as well. So how it relates to the coldest, I forget what you said, the coldest point in the month or something like that, I'm not sure. I'd have to think about that, but chilling definitely plays a role.
Yeah, worth a conversation with Dave Goodori to figure this out, but maybe we can do that sometime. Our plant pathologist here at Geneva.
Okay, thanks, Jason. Tim, if you are ready to get started, you can go ahead and take off. I think I've given you control of the slides. So.
Okay, well, thanks. I want to thank Jason for his presentation. We're very lucky at Geneva to have, I think it's 4 grape geneticists working on various projects on our campus at Geneva with us, and it really certainly adds a lot to what we do, and I hope the feeling's mutual with them. And so Jason is a great example of a scientist that really interacts with us a lot and is doing a lot of very, very practical and far-reaching work related to genetics and response to these complex things like cold injury. So what I'm going to do today is I'm going to have a talk that's maybe a little bit the opposite of what Jason has, and this is purely me talking about what happened during the growing season at our site up in Clayton, New York. As part of the Northern Grapes Project, we've been since 2012, we've been doing some trials up in Clayton, New York, which is right off of the St. Lawrence River, where it runs into Lake, where it drains Lake Ontario. So this is a new place for us that if you'd asked me 10 years ago, can you grow grapes up there? I'd have to say, well, you're nuts. But really, the northern grape cultivars have come in and really made it possible for them to grow grapes up there. So we've been working with a grower up there called Coyote Moon Vineyards, and we've done 4 seasons so far of trials. And during that time, several things have happened. In the winter of 2013, 2014, it got down to minus 36 degrees, and so we had a lot of winter bud injury. This past winter, we didn't have that sort of thing, but we did have a late spring frost. So I'm going to talk about the consequences of that and what happened this year as a result of a late spring frost we had on May 22nd and 23rd. This is very late for frost to occur by our standards. Typically, when we get a frost, the grapes might be out, 1 or 2 leaves. But when this occurred, we had 3 to 6 inch shoot growth, and the grapes were already out. So what I want to do is talk about how this affected the phenology, the timing of the vine development, and I want to present a comparison of what happened with the first crop, that is the shoots that survived the frost on May 22nd, and then the second crop, which is the shoots and the grape clusters emerging after the frost. We tracked both of these over the summer because as a consequence of this freeze and in order to get some data out of the trials that we're doing there. So principal question was, well, all right, our first crop is, sort of gone, and so is the second crop going to get ripe enough? Can we make wine out of it? And then the third thing I want to talk about briefly, and I'm not going to give you any illusions that there's much you can do for management, but there are a few things that you can do, and a few things that really came out of seeing this experience up in northern New York, both at Coyote Moon and a number of other vineyards around the site. Okay, so what we have is a training study up in Clayton, New York, where we're comparing 3 different training systems. Vertical shoot positioning with a mid-wire cordon, and we follow that up with intensive canopy management, leaf removal, shoot tipping, that sort of thing. And comparing that to a simpler management system where we have the grapes trained to a high cordon or top wire cordon, and the only canopy management we do aside from thinning shoots on that is we try and comb the shoots down to improve the light interception up at the top of the canopy. And then the third one is one that I wanted to try because I didn't see anybody growing these cultivars using a cane prune system. So we tried a very traditional system, umbrella niffin, which consists of 3 or 4 long canes and is trained with a head in the middle. So this is the experimental setup we have, and we follow this every year with yield and fruit composition data. Okay, so I want to walk you through the season here, and just I have several photos here of how things looked. Here's in mid-April when we had just finished pruning, and we're taking pruning weights off of the front neck block. And I'm not going to talk about Marquette today very much, although we do have similar plots with Marquette. So in mid-April it looked like this, and there wasn't any bud swell at this point, but come back a month later on May 14th, and the shoots are already out 3 to 5 inches, and we left a lot of buds there and longer spurs with the thought of coming back and adjusting the shoot number later on in the season. So here's just another shot looking down at the umbrella niffin on the left and the high cordon on the right. So we got a good complement of shoots out there by the middle of May, with bud bursts probably occurring somewhere in the first few days of May, which is typical for our region. Now on May 18th, we came back to Clayton and we did shoot thinning to adjust the shoot numbers to approximately 4 or 5 shoots per foot of canopy. And here's the before picture, and this is the after picture. So before and after. So we did remove quite a few shoots off of these vines and felt like we were ready for the growing season and following these vines as we normally do. But then the freeze intervened, and so this is what the same vineyard looked like on May 25th. And you can see on just about every vine there might be 2 or 3 or 4 green shoots, but the rest of it was totally frozen. And this is quite unusual for this to happen this late when the shoots are out that far. Typically it's after bud swell or just a little bit after bud burst. And typically in my experience it's not nearly as complete as this freeze injury was. Okay. So here's the situation. We might have a couple of shoots there, and this is the end of May. These are ready to bloom in a couple of weeks, but there's only a few of them. And then we see all the dead shoots, which were actually rotting on the vine and had a little botrytis coming in because it was a very wet June. So around that time, May 28th, that's the first visit in which we saw then the latent buds emerging. Some of these were secondary buds coming from the same place where the original shoots had been, but others were latent buds that came out of nodes that hadn't pushed before, and particularly the cordons. And this is where you'll see later on in our cane prune system, there are no latent buds. There's just the buds at each node position. So so that definitely had an impact on how many shoots came out after the freeze. So here's late May. We're just starting to get the second growth. And the question was, well, how much of this is going to have actual clusters on it? So fast forward a little bit to June 15th, and that's about the time when the first crop, as we're referring to it, the shoots that didn't get frosted, the clusters on them were starting to bloom. And then, but you can see that the canopy is starting to recover there. And here's, I took a sample of different shoots, and you can see on the left we had some that were very well developed at bloom or just past bloom. And if you look over to the right, then we have these second crop shoots. Hang on, I'm trying to get the pointer here. Okay. Yikes, I don't like that. Okay. That were much less developed and just at 3 to 6 inch shoot growth by the middle of June. So what we decided to do, because we aren't going to be able to collect our normal data out of that, is Kristin went through and tagged all the shoots that had clusters from the first crop on them that we could still distinguish at this point. And so from that point on in the season, we followed the development of the first crop clusters and the second crop clusters. So that's the terminology I'll use. So by the end of June, what we could see is that we had some shoots from this first crop that had pea-sized berries already. whereas from the second crop, we're still looking at something that really hasn't, is still a couple of weeks away from bloom. By the middle of August, however, you can see that the canopy recovered, and this definitely shows the recuperation power of Frontenac to respond to the freeze injury by pushing out a new canopy. But when we looked at the clusters, again around August 15th, we were starting to see veraison on the clusters from the first crop, but then these second crop clusters were still green in the middle of August and still a ways away from veraison. And still at the end of August, we saw the same thing. A lot of the second crop clusters, although they're quite sizable and well developed, they still hadn't been through veraison because of their development being delayed. So by the middle of September, they pretty much all turned, but I'd like to point out to you that then this leaves you with two different populations of clusters, some that develop 3 weeks later than the other ones, but it would be impossible to go through and say, well, these are first crop, those are second crop, because they all look the same. They've all turned the same color. And yet they might have very different fruit composition. So we harvested this on October 9th, and we separated out the ones from the first crop and the second crop and weighed those and counted those separately. And what we do when we harvest the vines is we count the clusters as we pick them, and then we weigh them and calculate cluster weights and berry weights, and then do fruit composition on the different treatments there. So here's what they look like at harvest. The first crop is on the right. Many of these had started to desiccate a little bit, and some of them, particularly the ones that were farther inside the canopy, had gotten a little bit of botrytis, which is very unusual for these varieties. But all in all, you can see that it would be impossible to really tell the difference between these clusters just by looking at them. So you couldn't say to yourself, well, I'm just going to harvest those more mature clusters and leave the other ones hang for a couple of weeks more. That would be an impossible thing to do. So just to summarize, the consequences in terms of the phenology between the first and second crop. What we saw for bud burst was about a 4-week delay from the first crop when the freeze happened in late May. So about a 4-week delay in bud burst, and then subsequently about a 3-week delay in bloom, and then veraison was delayed by 2.5 to 3 weeks. And of course, we harvested them both on the same date. So here's what we came up for yield, and as you can see from this, the first crop, we had an average of 1.8 to 3.1 shoots per vine, and about 2/3 of those had clusters on them. So had we had a full crop on there and they had not been frozen out, we would have certainly had a full complement of clusters on there. Hang on. Okay, for the second crop, then we had a lot more clusters per vine. You can see in the high cordon labeled TWC there, 43 clusters per vine on the VSP 20 and 18 on the umbrella Niffen. And again, the fewer clusters is probably a consequence of not having all those base buds, those latent buds that you find on cordons that remain latent for several years and then can emerge. You don't have those on cane prune vines. But looking at the cluster size, the second crop clusters were just as big as the first crop clusters. And instead of 60 or 70% of the shoots having clusters on them, we had between 30 and 38% of the shoots having clusters, with more on the high cordon training system, likely because those were more exposed to sunlight being at the top of the canopy. Okay, so just to compare that to 2013, which is the last year we had a full crop, this vineyard was able to produce 4 to 5 tons of grapes, or 14 to 16 pounds. I had 60 clusters, and the clusters weighed about 100 grams and had 90 berries. So these clusters were a little smaller, but you can see on the high cordon that really the grower got almost half a crop on the high cordon, and maybe a quarter or 20% of a crop on the other 2 training systems. So that's not terrible. So the other question then is, what about the fruit composition? So I'm just going to put this all up there. And the first crop, bricks got up to 23.5. The second crop, basically 1 degree of bricks later by harvest. But you can see that the titratable acidity was lower on the first crop, about 4 grams per liter lower than on the second crop. And the pH was a little bit higher on the first crop than on the second crop. So all in all, the second crop didn't quite catch up. And those are pretty high titratable acidities at the end of the season. We did follow both the Frontenac and the Marquette, do a time series from late August through October, 5 or 6. And you can see the trends here with the soluble solids on the top left with Frontenac, that they started out far apart, but then they kind of caught up by the end of the growing season. Similar thing here with the Marquette, that they start out a lot lower, but then accumulated pretty much at the same rate and only ended up about a degree of bricks different. With the titratable acidity, again, here the yellow line is the first crop, and you can see a typical curve there. And then the second crop just, did decline, but not nearly to the extent so that at harvest we had, 4 grams difference in acidity. And on the Marquette, we had about, 2.5 degrees different. That said, the grower was able to harvest the Frontenac and the Marquette. And with the Frontenac, he told me that he's making a semi-dry wine with enough residual sugar to balance out the acidity. And he says that he came in at harvest overall in the blocks he harvested at about 17 grams of acid, which is not totally out of the question for Frontenac. I only have a few things to say about management, and one is the result of visits I made not just to this vineyard, but to 11 other vineyards up in the Thousand Island area. The entire area was hit, but out of the 11 vineyards I visited, there was 3 standouts that were planted on hillsides that had very good air drainage, and those largely escaped damage. Now this is at Coyote Moon, but you can see even the slight rise up towards the end that the higher part of the vineyard got a lot less injury than the lower part. Saw this also in the Finger Lakes where low areas of the vineyards that typically produce stuff were definitely more injured than the areas on the hillside. Okay, so almost done here. And the last thing I want to talk about is something that I've done over the last several years is I've gone to different vines, and from the same vine I've picked clusters that are exposed and clusters that are shaded at the end of the season. We take them in, 25 clusters of each, and individually analyze them for fruit composition. And what you can see here is that the exposed, in terms of bricks, the range of bricks is much tighter on the exposed clusters than on the shaded clusters. The shaded clusters have a much wider range. The titratable acidity is definitely lower on the exposed and again a smaller range than on the shaded clusters. And that's not just this year, but I've done this over the last couple of years. Oh yeah, and we were able to do tartaric and malic splits, and I don't know what this means exactly, but you can see again exposed clusters, more tartaric acid in general, or a tighter range of that, and less malic acid, so lower amounts of malic acid. Again, we've done this over the last couple of years. I just want to show you this briefly. Here's what we found in 2013 when we did this on all three training systems. Looking at the bricks, the exposed clusters, higher bricks than the shaded clusters, and titratable acidity, again, lower on the exposed clusters. And finally, just to beat this into the ground here, here's one we did on Marquette in 2014. Again, saw the same trends, higher bricks on the exposed clusters, lower titratable acidity. So if your goal is to manage titratable acidity, regardless of the training system you have, it's good to have that fruit exposure. And even this year in our second crop, we were able to, had we exposed all the clusters, that would have materially influenced the acidity and minimized the acidity. Okay. Okay, so just to summarize, this season has really convinced me of the importance of site selection. Good air drainage is very important. You can put fans up or wind machines, and several growers are thinking of buying them up there to mitigate this frost injury. But if you have a poor air drainage, then you're likely to see a repeat of this in future years. So site selection, again, we always come back to that as a very important thing. But then the other thing you can do is try and provide good cluster exposure to sunlight by having the appropriate shoot density and maybe doing some leaf removal, because having warm clusters that are exposed to sunlight, it lowers the acidity, and the exposure also promotes drying and reduces disease incidence. So that's all I have for now, and I'd like to give a shout out to our field crew that helped us harvest and do some other stuff, Mike Colizzi, Steve Lurch, Bill Wilsey, Chrislin, who's done all the data collection and monitoring of this site, and then our cooperator, Coyote Moon Vineyard, the Randasses, who's done a lot of excellent cooperation with us over the last several years. So I see it's a little bit after 5, so I apologize for running late here, but Chrislin, do we have any questions?
Yes, we do. So the first one is from Austin Ferguson, who asks, please give a short list of ways that Marquette differed from Frontenac. And this was before you got into the fruit chemistry and everything.
Yeah. What I found over the past several years is that Marquette tends to break bud a little bit earlier than Frontenac. What we found following the freeze in 2014 was that the Marquette came back with pretty much a full crop, but suffered a lot of trunk injury after our Arctic vortex blast of 2013 and 2014. Whereas the Frontenac that year, pretty much all the primary buds were killed, and the secondaries didn't come back with very much fruit. So we had a low crop, but the trunks hung in there, and they're still very good. So you know, in terms of the cold weather, what we've seen is that the trunks of the Frontenac were more sensitive, but the secondary and tertiary buds that came out in 2014 seemed to be more fruitful than the Frontenac, whereas the Frontenac, the vines, the trunks survived better.
I think you had a little misspeak there, that the Marquette trunks are more sensitive to cold.
Thank you, Kristen.
All right.
It's getting late.
I know, and I think another important thing to note is that generally Marquette gets better fruit chemistry by harvest than Frontenac. The acids drop more in than Frontenac, at least at this site. So
yeah, right. Yeah. Marquette tends to have a couple grams less acid at harvest than the Frontenac does.
Yeah. Okay, then Jack asked, in hindsight, would you recommend culling the second crop and just letting the first crop ripen fully?
I'm sorry, I missed that.
Jack asked, in hindsight, would you recommend culling the second crop and just letting the first crop ripen fully?
Yeah, well, if they'd done that on the Frontenac, they really wouldn't have had any crop. So that would have been perhaps a way to have the vines recover a little bit more, but there wouldn't have been any fruit out there. So so in hindsight, sure, that might be a thing to do if and just say, well, I'm not going to have a crop this year. And it will be interesting to see what this fairly heavy but late developing crop, what happens next year with the buds. Are they going to be less fruitful? Are we going to have carryover effects? And I don't know the answer to that.
I don't know. I mean, the canopy on the Frontenac, though, did look really good. I mean, there was a lot of vegetative growth out there still. So I don't know, you know, just wanted to throw that out there, that the canopy looked really nice in the Frontenac despite how awful it looked after the frost. Okay, then Austin asked, Austin Funk, we have two Austins on tonight, asked, so are we talking leaf pruning, shoot positioning? What is the holy grail to get the acid down and the bricks up?
Well, my opinion there is that you start with a high cordon, and if you can do it, and this is a little bit tricky to do timing-wise, if you can then go through and comb the shoots downward, that's going to maximize your fruit exposure. If you really want to spend the time, you can certainly do leaf removal up at the top of the cordon. It's a little hard to do mechanically, and I don't feel like it's fully necessary, but certainly the other thing to do is to make sure that you have appropriate shoot density. So instead of having 7 or 8 shoots per foot of canopy, you want to bring that down to 5, 4 or 5 or 4 or 5 or 6.
Yeah, and some of the researchers at Iowa State who are involved in the project have been doing some more of this canopy management stuff like leaf pulling and shoot thinning and looking at the effects on fruit chemistry. So That information, if you go to the Year 3 Progress Report on our website and go to the studies from Iowa, you can see some of the information that they've found. Okay, then Jack asked, how soon in the cluster life would you expose the clusters to sun? Pea size?
Yeah, right after fruit set seems to be the appropriate time to do that. If you do that later on, then you might end up with more sensitive berries that are more prone to sunburn.
Okay. And then one last question from Link, who said, is this an argument for using cordon pruning versus cane pruning?
There's definitely arguments on both sides. What we're finding here with the umbrella niffin is certainly you have to spend some extra time tying those. On the other hand, if your nodes are properly spaced, then you don't need to do as much shoot thinning to come up with a canopy of the appropriate density, because you're not going to have any latent buds come out. Whereas on a cordon, you might have several shoots bunched up in a single area. Now this year, that obviously worked out well because of the freeze, that we had a lot more shoots push from the cordons than we did from the cane prune vines.
Okay.
But that's only if you get that sort of spring frost injury.
Yeah, so Link followed up and said the question was, do you do cordon pruning so that you can have latent buds? I would say if you're in an area that's very prone to spring frost, then that might be a consideration when you're choosing your training system.
Yes.
So, yeah. All right. Well, Tim, thanks. That got through all the questions.
Okay,
so
thank you very much for attending. It's been fun.
Yeah. All right. So thanks, Jason, and thanks, Tim, for your presentations, and thanks to everybody in the audience for your questions. It always makes the webinars a lot more interesting when we get a lot of participation from the audience. So thanks for that. I also I put up the schedule of the upcoming webinars, the ones that we have scheduled for 2016. You'll be getting emails about those as I open up registration, and then you'll get if you're on the mailing list, you'll get the information on how to connect to each of those. So I think we got a great slate of webinars planned, so I look forward to that. Then I also wanted to announce that the Northern Grape Symposium is going to be held February 24th in Kalamazoo, Michigan. This is in conjunction with the Michigan Grape and Wine Conference. The full schedule is up online now, and listed below are the talks that are actually part of the Northern Grape Symposium. So anyway, it would be great to see some of you there. With that, I also posted the link to the post-webinar survey. If you wouldn't mind clicking on that link when we're all done here and going and taking the survey, we really do value your input, and we use your input just for our own information and then in our reporting to the USDA that is also very important. So if you could go take that survey, we'd really appreciate it. So again, thanks to Tim and Jason, and thanks to everybody in the audience. Good night, everyone.
Yeah, good night.
Night.